Could we bring back Voyager 1? When will we get a deep field exposure from James Webb? And why is Europa Clipper using solar panels? All this and more in this week's Question Show. Hey everyone, welcome to the Question Show. Your questions, my answers. We are back after our summer hiatus with a fresh season of questions and answers here on the channel. So as always, if you're on my channel, a question pops in your brain, just find the nearest available YouTube comment location and put in your question. I'll gather a bunch of them up and I will answer them here. All right, let's get into the questions. Henra99. A question for the Question Show. As ridiculous and as insanely expensive as it might be, what would it take to bring back Voyager 1? Would it be technically possible using chemical rockets? So it would be incredibly difficult to bring back Voyager 1. This spacecraft is tens of astronomical units away from us, like beyond the orbit of Pluto. It is moving on an escape trajectory out of the solar system. And so to be able to actually catch it or Voyager 2 and bring them back, like Voyager 1 is the fastest moving spacecraft that humanity has ever sent out of the solar system, and it is never coming home. And so in order to be able to catch it, you would need to build a spacecraft that is capable of going faster than Voyager 1, but also is able to then cancel out the outward velocity and make a return voyage to Earth. In other words, right now, Voyager 1 is on an escape trajectory. It's going out into the Milky Way. You would need to slow it down to the point that it's going to now be on an orbit around the sun and fall back down into the solar system. Now, I haven't done the exact math on this, but I've done an interview with someone about similar math. And they proposed that if they wanted to try and bring a sample back from Oumuamua, a interstellar object that's moving on an escape trajectory away from the solar system, you would need about 100 kilometers per second of delta V. In other words, you would need to be able to, over the course of your mission, be able to change the speed of your spacecraft by about 100 kilometers per second. And that's a lot. Like the Earth is going 30 kilometers per second around the sun. We don't really have spacecraft that can cancel out that velocity. And so we need something that is beyond what we currently have. And no, a chemical rocket probably wouldn't do it, especially because Voyager 1 is going to weigh, a few thousand kilograms. And so it's not just like a teeny tiny sample off the surface of Oumuamua. You're trying to bring home thousands of kilograms from the outer solar system. So you would need that 100 kilometers per second of delta V, and you would need to be able to move thousands of kilograms of mass at that amount. So what kind of machine would do this? And so the spacecraft that they were proposing to be able to do the sample return mission from Oumuamua was essentially an RTG, radioisotope thermoelectric generator, the kind of thing that powers Perseverance and Curiosity and the Voyagers and provides electricity. And then you would bolt it to an ion engine with enough fuel to be able to make this journey and pretty much nothing else. It's just going to be like a hot rod, which is power source, propulsion system, nothing else. And you could reach Oumuamua, you could grab a sample, you could bring it back home. But then you need a scaled up version of this. You need something that is, like Starship-like in the size of the RTG, the size of the propulsion system, the amount of fuel on board to be able to chase down Voyager 1. So, is it possible? Yes. But it would cost like the gross domestic product of most of humanity to be able to do this. We could put it in a museum and say, we did that. Even though it was a waste of money, we brought Voyager home. Now, after that first question, you might have noticed the Stargate planet name that appeared above my shoulder. And this is a way for you to vote, for you to tell us what you thought was the best question this week. Now, this is the first episode of the new season, and so we don't have any votes from last week. So instead, just go ahead and vote. What you do is you watch the episode and you'll see different Stargate planet names beside each one of the questions, and then go down into the comments and put in the name of the question that you thought was the best. And then we will count them up. And next week, we will be able to count up the votes. All right, so don't forget to vote. Don't act like you don't know Why does it seem like great hubris that nobody's asking for a true long exposure deep field from JWST? I want to see dim early galaxies, not only the brightest ones. Does anybody else? So the question you're asking is, why haven't they produced a proper deep field survey from the James Webb Space Telescope? And the way they've done this for the Hubble Space Telescope, in fact, they've done multiple Hubble deep fields. They started with their first version, and then they did another part of the sky, and then they did an infrared version, and sort of the final version of the Hubble deep field was like 100,000 galaxies, seeing some of them just a few 100 million years, like 500 million years after the Big Bang. It was, one of the most important photographs ever produced in the history of science. And are you asking if it hasn't occurred to astronomers that they should do the same thing with James Webb? It has absolutely occurred to them that James Webb would be a great telescope to produce a version of the Hubble Deep Field, the James Webb Deep Field. Now, on the one side, James Webb can do Hubble Deep Fields in its sleep. In a couple of hours, it can produce a picture that is equivalent to the depth of what took Hubble dozens of hours to be able to produce. It's just so fast. It's so big and it's so fast. But it is also incredibly busy. We are still only into a little over 2 years of use with James Webb, and there is just a gigantic list of projects that people want to use this telescope for. They're doing surveys of galaxies. It's called the JADE survey. There's another couple of surveys, and they're looking at galaxies that are early on in the universe. And in many cases, they're overlapping with areas of the Hubble Space Telescope deep field, so that you can kind of compare and contrast between what Webb can do and what Hubble can do. But then they're also using Webb for exoplanet research. They're using it for studying newly forming planetary systems. They're looking at active galaxies, star-forming regions across dozens of galaxies in the Virgo supercluster. So it is a very busy telescope. And so right now you've got a bunch of different groups that are doing various galactic research, each of which is doing surveys. And the way this is kind of working out is a lot of the content that they're doing with these surveys is publicly available. So it doesn't fall under the normal embargo that the detailed observations from Webb are sort of mandated by. And so a lot of people can go and access this and start to ask questions about galaxies, and the answers are in those data. But at the same time, you've got these different groups, these different collaborations, and they already are starting to talk about what a true James Webb deep field would look like. Because when at their appointed time, at a time of Webb's choosing, it will turn and gaze at a single spot in the sky for dozens of hours. But that is just a giant chunk of the science that it does. And so the people who are going to be setting up that deep field, they want to make sure that they can understand the data that is coming off the telescope. They want to make sure that they're ready to be able to process all of that information and make the best use of, say, 50 hours of James Webb time, 100 hours, 200 hours, right? And so they're being very careful about it. And so there are plans in the works that the different collaborations are starting to meet, starting to hammer out what that deep field might look like. And at some point in the next couple of years, they will do that deep field. And it will be like nothing else that's ever been done. It will be one of the most important pictures that James Webb has ever taken. And it will sort of take the new next place as one of the most powerful, most important photographs that humanity has ever taken. TJM McGuire 9417, 100% solar. Why? This is grossly unreliable. Why not RTGs? They've been powering both Voyagers since 1977. So this is a question in response to the news that the Europa Clipper just got its 100-foot long solar panels, 30 meters. And that these are the largest solar panels that have ever been installed on a spacecraft. They are so big because the light that falls on Jupiter is about 4% the light that falls on the Earth. And so they need solar panels that are about 25 times as big as the equivalent solar panels that what you would need here for a spacecraft that's orbiting around the Earth. And the first time this was tested out was with the Juno spacecraft. And they weren't even sure, would solar panels work that far away from the sun, even if you scaled them up by 25 times? And the answer is yes. Juno has been amazing. And so the point that you're making is, why don't they just install an RTG, right? A radioisotope thermoelectric generator. This is a decaying chunk of plutonium that is releasing heat. The heat is being used with a thermocouple couple to be able to do electricity, and then you can run the instruments on your spacecraft. You don't need these gigantic solar wings. Now, there's a couple of issues. One is that about a decade ago, the Department of Energy, which is the people who produce the plutonium that is needed for these RTGs, dialed down the supply. And so a lot of missions that were in the works that were going to use plutonium had to come up with a new plan. Juno was one of these. I think New Horizons was one of the last spacecraft to be able to get that last batch of plutonium. It's not like plutonium grows on trees. And so engineers started to work out plans for what it would take to build a solar-powered probe that could go out to Jupiter and even Saturn. There are plans in the works for building a solar-powered probe that will go all the way out to Saturn. And so when the mission controller sat down around 2013 and thought about what capabilities Europa Clipper was going to need, what its power requirements were, they looked at the kinds of power plants that were available to Europa Clipper and found that, in fact, going with solar panels was the less expensive, less risky option compared to an RTG. When you consider having to get your plutonium from the Department of Energy, that you're going to have to launch this thing, and there's always a risk of a launch failure with a block of plutonium that is going to space. So, when they did all the pros and cons, they came to the decision that they should go with solar panels. And if you disagree, then by all means, look through the technical documents and see sort of the decision-making process. Everything's out in public and you can sort of follow along what they did. And I think you might find that you agree with them. And I think this is great, right? We need to do the experiments. You're right. We know that RTGs work. We know that solar panels work and are very reliable. I mean, there are spacecraft that have been solar powered for decades and they're still working great. And now we know, thanks to Juno, that solar panels work out at Jupiter. So let's send more spacecraft and really hammer out and work out what are the pros and cons, what works, what doesn't work, where do these things fail. This is how we learn. JP, if it takes light years for photons to reach us, how do we know we aren't completely surrounded by developed alien worlds where the light isn't just visible to us yet? You're exactly right that it takes time for photons to travel from star to star. So the light that we see came from Alpha Centauri. It took about 4.5 years to reach us. When we look at, say, the TRAPPIST-1 system, it's decades ago. When we look all the way out to the center of the Milky Way, maybe the light has been traveling for 25,000 years. But the universe is old. I mean, the universe is billions of years old, and that there could be life on many different worlds, and they would have had billions of years to evolve. And so, what are the chances that, say, the civilization on Alpha Centauri, only developed the technology to communicate at interstellar distances 3 years ago, as opposed to 4 years ago, or 100 years ago, or 1,000 years ago, right? It's a very thin line on where they could be more advanced and we wouldn't be able to notice. How long has humanity been able to transmit into the universe? For, let's say, 100 years, we've been able to send powerful radio signals out into space. And so there is a sphere with a radius of 100 light years around the Earth that alien civilizations have been receiving our signals. There are tens of thousands of stars within a 100 light year radius of us. And so, any of those civilizations would have received our signals at any point from our development. Alpha Centauri, they received stuff that was 4 years ago, but the guys who are maybe 100 light years away, they just received those first radio signals. And so the universe is old, civilizations are probably old, and the distances to stars, even though they are much farther than we could try to travel, they're actually not that far when the speed of light is concerned. Shay88. Hey Fraser, do black holes ever merge? Since time essentially stops around an event horizon, do they merge or stay apart by an asymptotic boundary line? Yes, black holes do merge. And I think, what you're getting hung up on here is that the perspective of an outside observer that is watching something fall into a black hole is that person, as they fall into the enormous gravitational well of the black hole, as that sort of approaches infinity, we see them just get slower and slower and slower. And then they just pause on the event horizon of the black hole. And then they redshift out until they become invisible. But we don't actually watch them get torn up and disappear and go into the black hole event horizon. And that is our perspective as an outside observer. But what's really happening is that as the black hole is absorbing the material of a person falling into it, the event horizon of the black hole rises to meet them. It actually grows because the size of the event horizon is defined by the mass that's in the black hole. So the event horizon gets a little bit bigger. The person is absorbed into the black hole. And so the same process is happening when you get two merging black holes. You get these two merging black holes, they get closer and closer together. They experience time dilation as they're going around each other, but at the same time, their event horizons merge and they become this new, larger black hole. And obviously this happens because we detect the gravitational waves that are coming from merging black holes. Thanks to LIGO and Kagra and Virgo, we actually have evidence that this is happening, as well as the evidence coming from the pulsar timing array of merging supermassive black holes. So this process happens at every scale. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Stefan, John Nicholas, T-Dub, Spiderswap.io, Ron Sinai, Orlando Erickson, Louis-Philippe Breton, Martin Schieliff, Jeff Parsons, Trucking Astronaut, and Johannes Kepler. Join the club at patreon.com/universetoday. Samurai. So I got some of those Celestron 80/20 binoculars. They're great, but I need a tripod now. Any suggestions for something with good viewing angles? Like, do most tripods look directly up? In one of the last episodes, I recommended a good pair of astronomical binoculars. I use the Celestron 15x75s, 50x70. They make a bigger version that's 20x80, and I think they make like a 25x100. That's pretty heavy, and yet, you know, you've got a lot of magnification. You can see the rings of Saturn, you can see the moons of Jupiter, you can see bands across the surface on Jupiter, you can see all of the craters on the moon. A nice pair of astronomical binoculars is wonderful. But the downside is that they are heavy. And so if you're lying back and you're watching the sky with your binoculars, especially the big ones, then after a while, like, your muscles are going to start to shake and give out as you're going to hold this thing on target. And so a tripod is a great addition to add to a pair of astronomical binoculars. Now, I don't know exactly what pair you have, but typically they're going to have a tripod mount that is either under the binoculars. The one that I have is kind of weird. The tripod mount is sort of in between the eyepieces of the binoculars, and then you put in a special adapter that then you can attach it to the tripod. And any tripod is going to work, you know, because it's going to hold the weight of the binoculars. But the problem is that tripods, say camera tripods, things like that, they are designed alt azimuth. They go up and down and they turn left and right. But the Earth is tilted. And so you're going to constantly get stuff that's going to fall outside of the field of view, and you're going to have to go down and to the side and down and to the side to be able to get, like, where this really comes as a problem is you're setting up your binoculars or your telescope and you want someone to look through this so you can go, hey, here's Saturn, let's check out Saturn. And so you get it all nicely lined up. You've got a lot of magnification, so it's really big in the eyepiece, and then you sit back and you bring mom over to look through the telescope at Saturn, and it's gone. And she says, I don't see Saturn. And you're like, oh, hold on, it must have moved, or the Earth rotated. And so you do this jig back and forth constantly. And the solution is that you get a mount that has an angle that is the same as the tilt of the Earth, and 26 degrees, 23 degrees, 23. Anyway. And then your telescope, you can then, you know, there's manual ones. You can just like turn a knob and it will turn and follow an object at a speed of your choosing. And of course, there are automated ones. Now, there are automated mounts that are used for doing astrophotography, and they've really changed the way astrophotography gets done with DSLR cameras. You know, you've got these really powerful digital cameras with really like bird watching lenses on them, but you try to take a long exposure image of the sky and you're going to get star trails. And so instead you put it on one of these tracking mounts, and now the thing will automatically follow the motion of the Earth, and the stars in your scene will be completely frozen, and you'll be able to do nice long exposures. If you really want the right tripod, I would go that route, one that actually does tracking of the sky, and so that you can then find a scene that you want to look at, lock it in, it's tracking, you're looking through the eyepieces, and it will constantly keep it in the same field of view. And also you can then put on your digital camera and be able to take pictures of the night sky, like really nice long exposure images of the night sky. But I'm glad you got those binoculars. I hope, other people out there as well have gotten binoculars. Celestron, you're welcome. They're not sponsoring me, but I just recommend those binoculars. Billions and billions of stars. Fraser, can you please explain how some black holes rotate and some don't? I thought everything in the cosmos rotates. I don't know where you've heard that some black holes don't rotate. Every black hole that's been observed rotates. And in fact, most black holes rotate at the maximum speed that is allowed by the laws of physics. As they rotate faster and faster, relativistic concerns start to take over and put the brakes on how much faster they're able to rotate. It's about like 70% the speed of light. And so as material is falling into a black hole, it's going to increase the rotation speed. The problem is that a rotating black hole is very complicated, much more complicated than a black hole that doesn't rotate. And so generally when people are learning the physics about black holes, learning to calculate the event horizon and things like that, they imagine a non-rotating black hole. And then they learn the hard math, the one that includes a black hole that is rotating at relativistic velocities, that is torquing up the space-time around it, frame dragging, and all of the other, surrounded by an accretion disk that is also rotating at a different speed, and they're interacting. You've got time dilation. Like, it gets more complicated when the black hole rotates, and yet that is the reality. And as you said, everything seems to rotate, and black holes are no exception. Spaceman Spiff, if a civilization's presence could be lost after 1 million years, how do we know there wasn't any out in the universe at a point? Like, the evidence of a civilization on Earth, like if there was an older civilization than humanity, any physical evidence of that civilization being here would be absorbed by the planet. Now, obviously, we see fossils of various life forms. We're actually seeing just an absolute minuscule fraction of the sum total of all of the creatures that lived and died on Earth. And, the number of times you'll actually see a fossil is just teeny tiny. And so there's this theory that it's called the Silurian hypothesis, that in fact, if there was a civilization on Earth before us, if it was more than about 1 million years ago, we wouldn't really be able to find any evidence of their existence. And if we disappear, any civilization arises, if the octopuses arise as a intelligent civilization, they wouldn't find any evidence that humanity was here. Now, that's not entirely true, because now, we have probes on the surface of the moon. And so they would fly their octopusian missions to the moon, and they would find humanity's artifacts, and they would have questions. But you're asking, like, how do we know there aren't any out there in the universe? And, we don't know how many civilizations there are out there in the universe, and where they are, and how far away they are. And it really all depends on how loud an alien civilization is. If an alien civilization is like us currently, today, not more technologically advanced than us, then they are quiet. Yeah, we are leaking some amount of radiation into space with our radio communications and things like that, but it's not very much compared to a civilization that is using up the entire energy of their star. They are blasting radiation out into space. It's a very clear signature that they exist. And so really, it just depends on whether civilizations become quiet or loud. If they're loud, and this is the idea of the grabby aliens, right? That you've got these civilizations that are gobbling up star systems, that they are converting the star systems into a more useful form. Why have a star surrounded by planets when you can have a star surrounded by a shell of satellites that are harvesting the power? And then it would be in the infrared, and you would watch this bubble in space that was increasing over time as more and more stars were consumed by this giant civilization that's approaching us at close to the speed of light. And so, so far, there doesn't seem to be any evidence of loud aliens within the observable universe. Now, obviously, we're having to look back in time. And so we don't see loud aliens within 100 light years of us. So that's fairly recent. We don't see any loud aliens within a few tens of millions of light years of us. And so it might be that there are none in the observable universe, or it might be that they are advancing towards us at the speed of light. And at some point, their civilization, their empire will sweep past the sun and the solar system as they continue to conquer the Milky Way. So far we just haven't seen anything. Avo 3rd, when the Earth's magnetic poles change, will the Earth be more susceptible to solar flares and the risk of the polar ice caps melting and flooding the Earth? So just like how the sun's polarity switches on an 11-year cycle, the Earth's magnetic poles flip on a longer cycle. I think it's about 700,000 years. And so what is the north magnetic pole becomes the south magnetic pole and vice versa. And we don't know when this will happen next. It seems a lot more random than the sun's sort of absolutely dependable 11-year cycle, but it will happen at some point. And it has happened countless times in the past. When you think about how many times you can fit, say, 1 million years into 4.3 billion years, right? It has happened thousands of times and will happen for thousands of times into the future until the sun consumes the Earth when it turns into a red giant. And so the question you're asking is, will this be bad? And the good news is there's no evidence that it's bad. That, when we look back through the fossil record and we match up the various extinction events that have happened, the great dyings, we don't see the great dyings matching up with when these magnetic pole flips happen on the Earth. And by the way, the technique that geologists use to be able to figure out when the poles of the Earth flipped is amazing. That essentially you have lava that is flowing, and it has some kind of magnetic crystals inside it. It's made of, iron crystals that are starting to cool and form as the lava is starting to cool down. And the crystals will align themselves with the magnetic field of the Earth. And then you'll get another lava flow that's over top of that happened after the magnetic flip happened, and now the crystals are aligned in a different direction. This is called paleomagnetism. And so geologists can actually track back, worldwide, every time the magnetic field of the Earth flipped. And then you've got the geologists, the archaeologists, the paleontologists that are working alongside them, and they've got all the times when we had 85% of the species on Earth die because of some event, and they sort of share notes and they don't line up. And so the good news is it doesn't appear that a magnetic pole flip causes life on Earth to go extinct. But it could be that radiation does increase. Right now we are protected by the Earth's magnetic field from the solar wind, from cosmic radiation. And if that magnetosphere is not like nice and stable, and instead is kind of mixed up and got various pockets and parts are being protected and other parts aren't, then you can imagine some localized increases in radiation that would be experienced on the surface. But no, you're not going to get the poles melting and all those kinds of problems. You're going to have increased rates of cancer, right? Because we're getting more radiation from space is sort of the kinds of things that we would expect. But clearly it's not enough to completely wipe out life on Earth. It's happened so many times in the past. Jonathan Allen, when will the first child be born off Earth? Obviously, we don't know. And right now, we're so new at this spacefaring thing that we don't know if having a child being born off the Earth is safe. That if a human body can carry an embryo to gestation, that if the birth can happen, if the first couple of years, which are very formative for life, in some level of less gravity, either you're in weightlessness, which we know causes health issues, or whether you're in lunar gravity, 1/6 gravity, or whether you're on Mars, 1/3 gravity, we don't know what the effects are on the human body or mammals or anything that gives birth right now. So there's a ton of research that is yet to be done. And so we're kind of waiting for those experiments to be done. Somebody needs to go, and either when a moon base is set up, someone needs to take mammals and have them gestate on the surface of the moon and find out what kinds of health complications happen to those animals. And then you do the same thing when the Mars base has been set up. If you want an answer earlier, you can set up some kind of rotating space station, a little tiny rotating space station that's only job is to create 1/3 gravity or 1/6 gravity for mice in space. Imagine that, giant rotating space station in 2001, but it's teeny tiny, and its only job is to provide some amount of gravity to mice. And then you let mice do what mice do, and you find out what the health implications are. And until we have performed those experiments, until we know the answer to this question, it is not wise for human beings to attempt this in space. And so I think, when you sort of consider the timeline, we have to have a base on the moon, and then we have to have a base on Mars, and we've got to have astronauts going to the moon and Mars on a regular basis. And then they're going to have performed these experiments with larger and larger animals, and eventually maybe primates, to find out what the health effects are on them. And then someone's got to be willing to take the risk of having children on Mars. So I think we are decades away from the first child being born in space. Longer. I don't know what's longer than decade time. Centuries? I don't think centuries. So I think 50 years seems safe to me. Stargate. When you talk about radiation in space, what kind of radiation is this? Can it be compared to nuclear radiation? Not exactly. So when we talk about radiation in space, we are talking about two kinds of things. I mean, there's more, but just in general, there is the protons that are coming from the sun that are accelerated to high velocity, as well as some other heavier ions, and they are hitting your body and they are causing damage to your DNA. But it's not like a piece of plutonium that is inside your body that is giving off alpha particles and causing damage to your body. These things are passing through. If you slowed them down, they would just be protons. And then the same thing with cosmic rays. Cosmic rays are particles that are being accelerated in supernovae, around supermassive black holes, from neutron stars, magnetars. And these are particles, mostly again protons, mostly just individual atoms of hydrogen that have been accelerated to 99% the speed of light. And so when that goes through your body, and it can take out a chunk of your DNA, and it's very hard to slow down cosmic rays. They have a lot of energy that is sort of equivalent. The highest energy cosmic rays, even though they are a single atom, can hold the energy of like a softball that's being thrown in a baseball game, right? Like there's a lot of energy there in these things. And so they are causing damage. And so like a lot of people wonder, like if you say you put something in to protect you from this cosmic radiation, like if you put ice around your spacecraft, put a meter of ice and that would protect you from all this cosmic radiation, would that ice become dangerous? Would it become radioactive? And the answer is no, that you've slowed down the protons, you've slowed down the various other ions so that they are sort of trapped in the ice, or have been slowed down to the point that they're no longer moving at relativistic velocities. They're not turning the ice radioactive. So it is different than a nuclear reactor, but it is still bad. The outcome is cancer if you experience too much radiation. All right, I'm going to give you some thoughts, but first I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Barry Lake Roofing, David Giltonan, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, SpiderSwap.io, Stephen Krasaki, Stephen Fowler Munley, and Vlad Chiplin, who support us at the Master of the Universe level. And all of our patrons, all your support means the universe to us. So when you're watching this is as we have returned from our summer hiatus, and we did an experiment this summer where we put up the overtime segments as question show episodes. We did 8, which hopefully got all of you through the summer. And I would just love your feedback. What did you think? Was this a great way to sort of keep the content rolling? Had you already seen the episodes because you're part of watching the live streams every week? And so it just felt like, I don't know, rehashed material. So I would just love to know what you all thought of that as an experiment, as a way to do this. We're always looking to come up with new ways to sort of entertain you and bring more content. And hopefully this worked well. It was fun to be able to kind of go back and revisit some of the older stuff and sort of see what my answers were and think about sort of as it relates. I tried to find stuff that was still sort of relevant and fresh, even if it was being watched up to almost a year later. So anyway, thank you everybody who watched this. I hope you had a great summer, and we'll see you next week.